So here we are in sections 23.4 and 23.5. We're going to look at sinusoidal waves as well as energy. So in a sinusoidal electromagnetic plane wave, the electric and magnetic fields vary sinusoidally in space and time. For a sinusoidal plane wave traveling in the positive x direction, the electric field magnitude is going to be the maximum multiplied by the sine of omega t minus kx. The same thing is going to hold true for the magnetic wave, except of course it's dealing with the maximum in the magnetic field. So the electric and magnetic fields each contain energy. The maximum magnitudes of the electric and the magnetic fields are related in this particular equation, which you may remember from the previous lecture. The intensity can be expressed here, and we will get to this relationship in a minute. And if you will notice here, the mu naught, or the square root of that, well, the speed of light ends up coming into the picture here a little bit. So we'll discuss that here in just a minute. Now, before we go over what's going on here in section 23.4, I kind of want to give a little bit of a study as far as what epsilon naught and mu naught mean. Now, probably the best way to try to remember what's going on there, the differences between those two, is that epsilon naught, you can think of epsilon starts with E and relates to the electric field. Basically, what we're referring to when we say E naught, that guy right there, we're looking at the absolute dielectric permittivity of a classical vacuum. It's basically the capacity of an electric field to permeate a vacuum. That's what this constant is dealing with. So E naught, you can think of electric field, or E naught, epsilon naught, electric field, everything starting with E. So how difficult is it for us to have an electric field that permeates a vacuum? Mu naught, on the other hand, is going to deal with a magnetic permeability of a classic vacuum. So mu naught, that's the Greek letter mu. So mu naught, think of a magnetic field. Mu starts with M, magnetic starts with M. And so it discusses how permeable that vacuum is for allowing a magnetic field to form. So it's kind of a way to gauge, it's kind of a way to establish how difficult it is to produce a magnetic field in those conditions. So that's a good way to try to remember those two. And I know sometimes, when you think about it as you go through, you may not necessarily think of those particular concepts, but they're very important when you're discussing electric and magnetic fields. So now we're going to take some of that information here. We're going to go through the sinusoidal waves. These sinusoidal electromagnetic waves, they're very much analogous to the transverse mechanical waves that have been studied previously. It's just these waves don't need a medium to travel. They are at any instant in time, the spatial variation of the fields is also sinusoidal. So some sinusoidal electromagnetic waves share with the primitive wave, as we discussed in 23.2, the property that the instant the fields are uniform, at any instant the fields are uniform over any plane perpendicular to the direction of propagation. That is considered to be a plane wave. Remember that plane that was moving through in the previous section? That's what we are referring to here. The entire pattern travels in the direction of propagation with speed c. The directions of E and B are perpendicular to the direction of propagation, so the wave is considered to be transverse. The relationship here between the speed of light c and the frequency and the frequency and then the wavelength, you can see that relationship here. So if we need a wavelength, all we have to do is rearrange this particular equation and we can come up with it. And that's what's going on here. Again, the right-hand rule gives the direction of B relative to E. If you'll remember, we point our thumb in the direction of the propagation of the wave, point our fingers in the direction of the electric field, and then the palm will face the direction of the magnetic field. So the one form of the wave function for a transverse wave traveling to the right along a stretched string is going to be reflected as this, or eventually this. Y is going to be the transverse displacement from the equilibrium at time t. The quantity A is the maximum displacement or amplitude of wave. This is going to be the angular frequency, equal to 2 times the frequency of f. K is going to be the wave number, or the propagation constant, equal to 2 pi divided by lambda, which is where this is coming from. So if E and B represents the instantaneous values of the electromagnetic fields, and let E max and B max represent the maximum fields or amplitudes, then the wave functions are going to be as denoted here. The negative sign is for a wave that is traveling in the x direction. The positive sign is for propagation in the minus x direction, which kind of runs counterintuitive to what you might fully expect as you go through. Capital T is going to be the period of the wave, and lambda is going to be the wavelength. Omega, of course, is going to be 2 pi divided by t, and k is going to be 2 pi divided by lambda. E max is going to be equal to c times b max, and when E is positive, B may be positive or negative. Determine the sign by using the right-hand rule. So again, here, the right-hand rule gives the direction of B relative to E. If you take your right hand, point your thumb in this direction, point your fingers in the direction of the electric field, you would see that the magnetic field would point that way. Doing the same thing over here, you would see the magnetic field pointing this way. Over here, back again, your magnetic field would be pointing in that direction. So you've got several problems here that I would recommend that you go through. Now, let's go to section 23.5. So energy is associated with electromagnetic waves. You can think of the sun's radiation, the radiation of microwave ovens. To derive detailed relationships, we begin with the expressions for energy densities, or energy per unit volume in electric and magnetic fields. These expressions show that the total energy density U in a region of space are present by the following expressions. The energy density in a region of empty space where electric and magnetic fields are present is going to be this. So the energy regarding the electric field is going to be here. For the magnetic field, you're going to see it here. The two fields, of course, are related by this particular equation, which we've gone over before, and that is equal to this. You combine this equation with 23.5, we're going to express the energy density in the following ways. And as it turns out, you can express the energy density in terms of the electric field alone, since you can take the magnetic field and express it in terms of the electric field. So it makes it a little easier. The units, of course, are going to be joules divided by volume, which in this case is going to be meters cubed. The energy density associated with the electric field is equal to that of the magnetic field. And mu, not mu, but U oscillates in time due to the fact that E is sinusoidal, which would make sense. So the electric magnetic fields advance in the positive X direction into regions where originally no fields were present. So it's clear that the wave transports energy from one region to another. So we can describe this in terms of energy transferred per unit time, per unit cross-sectional area, or power per unit area. Since power is going to be defined as the energy divided by time. So for an area perpendicular to the direction of the wave travel, that's one way we can look at this. The average value of this quantity is called the intensity of the wave. To see how the energy flow is related to the fields, we'll take a stationary plane perpendicular to the x-axis, coincides with the wavefront at a certain time. At time t, after this, the wavefront moves a certain distance. In other words, speed multiplied by time is going to give you the change in the displacement. So consider an area A on the stationary plane. We know that the energy in the space to the right of this area must have passed through it to reach the new location. So whatever this volume ends up having to be here is going to be the area multiplied by the length, which again is going to be this. So the change in the energy in this region is the energy density, U times whatever this volume happens to be. So this energy passes through the area A in time t, or delta t, the energy flow per unit time per area, which is denoted by S. So using some equations, you can derive alternate forms of this as you go through. And what you find out here is that the units of S are energy per unit time per unit area, or power per unit area. E and B are generally instantaneous values of the electromagnetic field amplitudes. So for a wave in which fields vary with time, S is also going to vary. That makes sense. The average value of S is the average energy transmitted across a given area perpendicular to the direction of propagation per unit area per unit time. In other words, the average power per unit area. So for a sinusoidal wave, the average value of E squared is 1/2 the square of the amplitude E max. And so in this case, we can find the average value by replacing this with that. And as it turns out, these are the equations that we come up with. If we make some more substitutions, we find out that our average energy density turns out to be this. Comparing that with the equation 23.8, we find out that these are related in this fashion. So this again is another way to state that. It's the average does not vary sinusoidally, which that would make sense. So anyway, those are some good equations there. Now, radiation pressure. The fact that electromagnetic waves transport energy follow directly from the fact that energy is required to establish electric and magnetic fields. It can also be shown that the electric waves carry momentum with a corresponding momentum density. So for a sinusoidal wave, the average value of E squared is E max squared divided by 2. The average momentum density ends up, if you do the replacements here, ends up being this. The momentum of an electromagnetic wave, which is kind of hard to think about, but that's what we've got, is a property of the field. It's not associated with the mass of a moving particle. There is a corresponding momentum flow rate equal to the momentum per unit volume multiplied by the wave speed. And that turns out to be this. Again, the flow rate is going to end up being the change in momentum with a change in time. This is responsible for the phenomenon of radiation pressure. So when an electromagnetic wave is completely absorbed by a surface perpendicular to the direction of the propagation, the rate of change of momentum with respect to time equals the force on the surface. So the average force per unit area, or the pressure, is equal to the intensity divided by the speed of the wave. If it is totally reflective, the change in momentum is twice as great, and the pressure is this. So for example, the value of I for direct sunlight before it passes through the Earth's atmosphere is about 1.4 kilowatts per meter squared. Corresponding radiation pressure on a completely absorbing surface ends up being this number of pascals. The average radiation pressure on a totally reflecting surface is twice that. And these are very small pressures on the order of this, but they can be measured with sensitive instruments. So those are those are some interesting concepts that we can take forward about electromagnetic waves.